Last topic of Unit 4, Trajectory Planning. Robots are involved in pick and place operation, assembly operations, loading, material handling, weldings, etc. etc. Now, all these operations requires a proper robotic motion. Path is a sequence of robot configuration in a particular order without regard to the timing of this configuration. Means they only describe the geometry of, geometry of motion. No timing is considered in describing the path. While trajectory considers timing also, so it concerns about when the path of robot reach to a particular position at what time. So trajectory is a smooth time function that describes how robot moves from initial to final position in the workplace. Trajectory planning can be done in joint space or in Cartesian space, which is also known as an operational space. In joint space, the description of motion is a function of joint variable like joint angle, joint velocities, and acceleration. So that's known as a trajectory planning in joint space. So if trajectory is a function of these variables, then it is a joint space trajectory planning. If trajectory is described in terms of end effector position and orientation, then we say that the planning is done in Cartesian space or operational space. So which variable you select, depending on that, two categories there. Comparison between the two types. Joint space planning, when we decide the trajectory in terms of joint angle, then motion between two points is unpredictable. It can go through any path. While in case of Cartesian space planning, the motion between two points is known at all time, can be controlled, but it can also be visualized. Second point, joint space planning, it can't deal with the obstacle present in the workspace because motion is unpredictable. While in case of Cartesian space planning, collision-free path can be obtained. Third point, joint space planning. In this trajectory planning, the inverse kinematic is computed only once. You know, inverse kinematics is computationally expensive. It involves the nonlinear equation. So here, it's required only once. While in case of Cartesian space planning, we have to solve kinematics equation at each step. So number of times we have to solve that equation. So it is computationally expensive. And in Cartesian space planning, it's difficult to ensure that singularity does not occur. So this is the comparison. Steps in trajectory planning. First, you have to plan your task, means what is your application and what type of motion you want or what type of action you have to perform. So that planning is required. Then according to that task, sequence of knot point in a Cartesian space should be decided. So you can say it's a key point through which the robotic arm will move. Then interpolation in Cartesian space. So more number of points can be added by a method of interpolation. So then you get a geometric path in Cartesian space. You sample this path and apply the inverse kinematics. So you go from Cartesian space to joint space. There you get the knot point in a joint space. Here you interpolate to get more point, means to get the smooth function. So you get the geometric path in joint space. So actual operation happens in joint space. So parameters required for trajectory planning are as follows. It requires the initial and final joint position, time interval to complete that motion, in how much time the motion should be completed, then initial and final joint velocities as well as acceleration. And then you can decide on which type of smooth function you select on the trajectory. Now let's see some example joint space trajectory planning. Here is the example of third order polynomial trajectory planning. It is also known as a cubic polynomial trajectory planning. So we required some parameters. So these are the parameters which already we know or we should have. Initial joint angle. So Ti initial time, the joint angle is theta I. Final joint angle Tf is theta f. Initial velocity, it is theta dot, so 0. Final velocity Tf at Tf 0. So we have 4 initial conditions. Now I am doing planning in joint space, so equation should be in terms of theta. So theta t is equals to, and which smooth function I have selected? Third order polynomial function. So this is the third order polynomial function. So here you have 4 unknowns C0, C1, C2, C3. But you also have 4 initial conditions. Now I differentiate this equation to get the joint velocity. So theta dot C1 C twice C2t plus 3 C3 t square. So after differentiating you get this equation. Again if I differentiate then I get acceleration. So twice C2 and 6 C3 t. Okay, so we get this acceleration. Now if you see from this equation, this is a cubic polynomial equation. This represents a parabola. And this is a linear relation. Now solve for 4 unknown using 4 initial conditions. You get all these 4 unknowns. C0 comes out to be theta I, initial joint angle. C1 is 0, C2 is this, and C3 is this. So you put this values of constant in this equation. So you get the equation of trajectory. So theta t is equals to this during interval 0 to tf. Okay, total time required to complete the motion. So this equation describes the motion of robot. Now, if you plot this equation, means joint angle, joint velocity, and joint acceleration equation, if I plot for a particular set of values, I get this type of graph. So from the graph, you can see this is the acceleration graph. It is a linear one, but uncontrollable. There is a discontinuity at the end point. Okay. Now, if you see velocity, it is parabolic curve. Zero velocity at end points, and this is the joint angle. So it's cubic polynomial trajectory. Okay. So here main issue is that acceleration is discontinuous at endpoint or uncontrollable. This is one numerical. Numerical is not expected, but if you have interest, you can go through that. Now, last point. We'll select another polynomial or a function for trajectory, that is cubic polynomial linear segment with parabolic blend. So this strategy is adopted in industry because it allows the verification whether resulting motion is supported by robot manipulator or not. Now here the trajectory is formed by linear segment connected by two parabolic segments at its initial and final point. Means in between there is a linear segment, cubical polynomial linear segment, and at the start and at the end we have a parabolic segment blended with the linear one. So because of this, velocity profile is not parabolic here, it is trapezoidal. You can see here, velocity profile is not a parabolic, it is a trapezoidal. And resulting acceleration profile you can see here. Now on the graph you can see here uh, this linear segment, and at the start and at the end you see this is the parabolic part. So this start end parabolic path is blended with linear segment. Uh, so what is special about this strategy? There is a zero acceleration in the middle where there is a linear segment, and you have a constant acceleration at the start and deceleration at the end. Okay, so acceleration problem has been solved. As far as velocity is concerned, there is a constant velocity in the middle part, and you can see increasing and decreasing velocity at the end part, means during parabolic segments. Okay, so this leads to a symmetric trajectory profile. You can see this is the middle point. So if you see on both sides, you see the similar symmetrical profile there. Okay. Now some constraints are required here. Some condition must be fulfilled, that velocity at the end of parabolic segment must be equal to velocity of linear segment. No issue, that is correct. And acceleration and velocity is subjected to given constraint. There is certain minimum value which these two variables should fulfill. Here you can see the velocity at the end of parabolic segment is equals to the velocity of linear segment. So they are matching here. Okay. So this is how the things are there as far as trajectory planning is concerned. Thank you.